Morning, folks. Good weekend, everybody. Yeah. All right, listen, I put your grades up on Friday. I'll give you a test back today. I also did put up the solution to them, so I'll give them back at the end of class. We're going to continue on with work like we started last Friday. Um, Remember, we will be having, not this week, but next week, we'll have an assessment in class. It'll be about 20 multiple choice questions. Uh, they'll be similar to what you've seen on the material up to this point. You might have a few questions about work and energy, which we'll have covered by then. Again, that goes towards extra credit in the class. It'll be a total worth a total of 20 points, a maximum of 20 points. And whatever points, whatever percentage you get on it, that's the percentage you get of that extra credit. So, I wouldn't spend a whole lot of time preparing for it, but before it, you might just want to sort of thumb through your chapters or thumb through your old test or whatever, the test that we took. They'll be mostly conceptual problems. There might be some very simple calculations, but um, I don't want to say it's going to be easy, but I want it to be easier than the test for sure. All right, let's see. We were looking at work. Remember, we define our work as the dot product of the force and the displacement. And remember, this dot product is a tool. It's a mathematical tool that it just allows us to take one vector and then multiply it times the component of a vector that's in the same direction, that's parallel and in the same direction. And the way we do that, well, we went through this business where we have I dot I, j dot I, and all those permutations. I dot I, for example, was equal to 1. J dot I was equal to 0. And that's based on the definition of our dot product, which is that it's equal to FD times cosine theta. And so I dot I, both of these vectors are parallel and in the same direction. So the cosine of 0 is equal to 1. And so when I multiply 1 times the cosine of 0, then that's equal to 1. Right? I times cosine of theta, that's equal to 1. Whereas j dot I would be 1 times the cosine of 90, and the cosine of 90 is equal to 0. So that's where that j dot I is equal to 0. Um, Likewise, we didn't do that here, but if we take two vectors, say I dot negative I, that's equal to negative 1. And you can think about that in terms of I in one direction, I in the opposite direction. The angle between those is 180 degrees, and the cosine of 180 is negative 1. Okay? Dot products, they seem a little funky right at first, but once you get the hang of them, it's really just sort of knowing these permutations, I dot I, J dot J, K dot K, those are all equal to 1, and anything else is equal to 0. You will see that on your exam, that you'll have a couple of vectors for force and displacement, and you'll have to take the dot product of them. What it means? All right, so we had looked at various vectors and how they do positive or negative work. So for example, we had a force that acts in this direction that causes a displacement in that direction, and that causes positive work. Whereas if I have a force in this direction and a displacement in this direction, that's negative work. That's similar to what we said over here about the I dot negative I. When we're talking about forces, we're going to be talking about the work done by individual forces, and then we'll also talk about the total work that's done by all the forces. So if I have, in this case, for example, I have a displacement in this direction and a force in that direction. There may be other forces that are acting on this object. In fact, there probably are other forces acting on it. But when I talk about the work done by an individual force, I'm just talking about that lone force. But sometimes we'll also ask, what is the total work? So you'll have a collection of forces, and you just add up the work. The other thing that we talked about last time on Friday was that work can have negative quantities, but a work is a scalar or a vector quantity. Scalar, right? In fact, the dot product is sometimes called the scalar product. The result of a dot product is a scalar quantity, always. We'll see that's in contrast to the cross product or the vector product, which we'll see in a couple of chapters when we get into rotation. All right, so this is a scalar quantity. So then what does it mean if my work has a negative value? It doesn't mean direction. Before, whenever we had a value that was negative, we said, well, this is a something that denotes direction. But when we're talking about negative work, the negative does not denote direction. What it denotes instead is that you're taking away energy from an object. So the work is going to be very closely related to the energy. If I do positive work, I'm giving energy to an object, whether that be kinetic energy or potential energy. If I do negative work, that means I'm taking away energy. Okay, those are all sort of things we covered on Friday. Um, I think we left off here when we were talking about gravity and does it do positive or negative work. Um, does gravity do positive or negative work? Do you think it does positive work? The gravitational force, does it do positive work or negative work? Right, it depends on the direction of motion actually. It can do either positive or negative work. If I have an object that's falling, right, that's going down in this direction, the force weight is in that direction. That's our gravitational force. Our displacement is in that direction. And in this case, our work is positive, right? Because our work is F dot D. In this case, both of those vectors are in the same direction, so it'll have a positive work. Whereas, or you can also think about this, that the change in kinetic energy is also positive. It's greater than 0. So I have a positive work, and I'm increasing the kinetic energy, right? On the other hand, if I have my force weight is up here, is in this direction, as it always is, but what if my displacement is in this direction, right? This is where I'm taking something and throwing it up, and before it starts coming back down again. In this case, what's happening to the kinetic energy? It's what? The change in kinetic energy is less than 0, right? So the kinetic energy is getting smaller. So here, my change in kinetic energy is less than 0. To put that in words, you know, the kinetic energy is decreasing. The change in kinetic energy is less than 0. And similarly, my work is also less than 0. I have a negative work here as well. So those two are closely related. In fact, we'll see that next, that they're, have we already done that? No, we're going to see that in just a minute. That these work and the energy of motion are very closely related. In fact, they're going to be equal to one another. All right, so the gravitational force can be either positive or negative work. Can either do positive or negative work, as all forces can. It just depends on the direction of the displacement. All right, let's try this. This is a quick little question. Just want to know, what is the work done by the shopper as this, she has a cart. She's pushing down on it with a 60-degree downward angle, like you usually do with a shopping cart, with a force of 40 newtons. What is the work that she does moving down a 25-meter aisle? All right, let's go about 10 more seconds. I'll stop at 145, 145. Okay, awesome. B is the right answer. Remember, our work is F dot D. That's the vector F times the vector D, the dot product. But the dot product is defined as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So it's going to be the force, which is 40, times the displacement, which is 25, times the cosine of the angle between them, which is 60 degrees. That's going to be 1,000 times a half, or 500 joules. So B is the right answer. Let's see some other answers that y'all put. If you put A, you just didn't do the cosine, right? You just did this force times this distance. But what you have to consider here is that I have a displacement in this direction, and my force is in this direction. This is my force, this is my displacement, this is the angle between them. And what you want to do is multiply that first vector times the component f cosine theta. You want to multiply these two vectors together, the displacement and the f cosine theta. So you left off that cosine theta term. Uh, it'll always be there, that cosine theta term. It's just when I have two vectors that are parallel, then it goes to 1, because cosine of 0 is 1. And then some of you put D, you just did sine instead of cosine likely. We had some funky stuff for the inclined plane where we switched up our angles, where we did the 90 minus the angle, but we're not going to do that at all with work. There's really not any scenario where you'll see that with work. It'll just be the cosine of the given angle. Okay? All right, let's get into the work-energy theorem. I've already addressed this a little bit, uh, but also kinetic energy. Kinetic energy is the energy of a moving object. Whether it's an alpha particle, electron, gas, molecule, whatever. The kinetic energy is equal to the 1/2 times the mass times the velocity squared. Let's just work a simple little problem to illustrate something. I'm going to show you, I'm just going to do this here in this space, but in just a second we'll talk about the work-energy theorem. It just says that any work that you do changes the energy. So let me show you just a simple problem with that. Let's say that I have a force equal to, I don't know, 10 newtons, and it acts over a distance of 20 meters. On a mass that is 4 kilograms. Right, so I have this force that acts over 20 meters over a distance of 20 meters on an object that has a mass of 4 kilograms. And I just want to know what is the velocity that acts on that object, or that object has after that force has been applied to it over 20 meters. Now, what we've done up to this point, you can work this problem, right? You could say, well, I know the force, so I can find the acceleration. So my acceleration would be like 2.5 meters per second squared. And I know it accelerates over 20 meters, so I can figure out the time that's required to cover that 20 meters. And then I can figure out, well, I can say V is V naught plus AT, and I can figure out the velocity. So that's a fairly, not a complicated problem, but it has several steps to it when you approach it from the kinematics, Newton's laws approach. But if we think about the work-energy theorem, it becomes a lot simpler. I can just say that the work is equal to the force times the displacement. Just assuming they're in the same direction, I didn't give you an angle. So that's 200 joules. And then I say, well, all of that work goes into changing the energy. All that work goes into kinetic energy. So I just say 200 joules equals 1/2 of the mass, which is 4 kilograms, times V squared. And that gives me a V equal to 10 meters per second. Right, I have a 2 here. I can divide through. That makes this 100. And then I take the square root of both sides. Square root of 100 is equal to 10. All right, that's a simple problem, but we'll have some problems that are slightly more complicated than that. That'll be more like what you have on your test, where I have this force that's acting over a certain distance, and then I can very easily find the velocity just by thinking about it in terms of energy. So we'll see a lot of the same problems. Like I think we might even we'll see some inclined plane problems and some various types of problems that you could have approached from a kinematics perspective, but they'll be a lot simpler when we think about it in terms of energy. Okay. I remember when we first, when I was taking this class and I got to this chapter, I really liked it because all of a sudden, all those complicated steps that we did for working kinematics problems, they weren't even necessary anymore because you could just think about it in terms of energy, and the problems just became a lot simpler. All right, let's see here. Oh, I have a little clip about Emily de Châtelet. She was a scientist in the 1700s, very early 1700s. Interesting because she was a woman in the 1700s as a scientist, and that just was not common at all. Um, and she also studied energy. One of the big contributions that she made was to describe the proportion between kinetic energy, or the relationship between kinetic energy and the velocity. And for a lot of time, people thought that the kinetic energy was just proportional to the velocity and not the velocity squared, despite evidence that they had otherwise, that it was proportional to the velocity squared. But they largely believed this because people in the time thought that squared numbers were evil, like they had some inherent evil associated with them, that they thought that Satan created these squared numbers. Like you might think the same too. I don't know. Do you? Sometimes I feel that way. But uh, obviously, people in the time they didn't really have a reason to be afraid of squared numbers, right? Because they used squared numbers a lot. What did they use squares for in the 1700s? Why did people use squared numbers or equations that had squares in them? Okay, yeah, Pythagorean theorem. But what did people do during the time in the 1700s, mainly to live? They were mostly what? They're mostly farmers, right? Because they're agrarian society for the most part. And farmers use square numbers a lot because they have to calculate yields for their fields, and so they have to know the area and of the fields, and then that comes into, how many seeds do I need per unit area and all that. So it's kind of silly, but it was superstitious, and we all have our own superstitions, I guess. Uh, but she showed that instead of the kinetic energy being proportional to the velocity, it's proportional to the velocity squared. And she had a very simple experiment. She had a substrate of clay, or just a bed of clay, and she would drop a ball from a certain height, from a height h, so that when it reached the bottom, it would have a velocity v. And, they had all the same kinematics equations that we have, and so they could determine what was the velocity. If I drop it from this height, they could calculate what is the velocity when it reaches that. And then she would measure the depth, I'll call it d, the depth d that this metal ball made into the clay. And then she would drop it from a greater height so that when it reached the bottom, it would have twice the velocity. And how deep do you think the ball went then? It went 4 times as deep, right? So if you think about this, if kinetic energy is proportional to the velocity, you would expect it to go just twice as deep. But she found that it actually went 4 times as deep, thus solidifying this idea that the kinetic energy is proportional to the velocity squared. It was actually a pretty big breakthrough for the day, that this idea that the kinetic energy is proportional to the square of the velocity. And again, the kinetic energy is not only proportional to the velocity, but it's also proportional to the mass. It's 1/2 mv squared. We have a little clip here about her. It's not really about her science, but it's just sort of about her life. Like I said, she was interesting just being a woman scientist, which was very uncommon at the time. I have a situation like this. I have 35 meters per second. I want to know its kinetic energy at the top here. Do about 15 more seconds, y'all. I'll stop at 2 minutes. I'll go to 205. 205. Okay, let's see. Hmm. The answer's C. What did y'all do to get D? Did you do cosine of 30 if you got D? Cosine 30 ever come in? No? Okay, let me show you how to do it, and then I think I know what you did wrong. Um, so I know our kinetic energy is 1/2 mv squared, but at the top, remember, my velocity is only in the x direction, and that's equal to vx. So for this particular problem, I'm looking at the velocity in the x direction only. So it's going to be 1/2 times the mass, which is 0.2 kilograms, times the velocity, which is going to be 35 cosine of 30. You have to be careful to square that whole value, and that's equal to 92 joules. Let's see what y'all did. That's 0.1. Yeah, so if you put D, you just didn't do the cosine 30 at all. Uh, so that's not right. The C is the right answer, just because you want the velocity at the top of the trajectory. And while it did have a velocity down here of 35 meters per second, it has a velocity here of some fraction of that. That's just the x component. So it did lose kinetic energy as it goes from here to here. Where did it lose that kinetic energy? What force acted on it to take away that energy? The gravitational force. Remember when we have an object going up and the force is pointed down, it does negative work. And so the gravitational force has done negative work. The amount is going to be the difference between whatever, well, we could find out the amount. It's going to be 1/2, that is the work done by gravity, will be 1/2 m times 35 squared. That's the kinetic energy that it has right here, minus 1/2 m times Vx squared, which is this work. So that would be 0.1, 1225 minus 92 joules. Wait, no, that's not right. Sorry. 123 minus 92. 8 plus 23 is 31 joules. So that's the amount of work that's done by gravity. It's a negative value. You follow what I did there? The amount of energy changes at the bottom part. It has a value equal to 123. That's just 1/2 times the mass times this velocity squared. The amount of energy that it has up here is smaller because it's now going a slower speed. It has 92 joules up at the top. And the work then that's done by gravity is just the difference in those two values. We're going to see that soon. It's going to be important when we're calculating gravitational potential energy. All right, so we've sort of been hot-footing around the work-energy theorem all along. It just says that if you do work on an object, I change the energy of that object. So if I do work on an object, I change energy. If you do positive work on an object, you increase its energy. If you do negative work, you decrease its energy. And up here, the work done by the gravitational force was less than 0. It did negative work. All right. Let's do a few clicker questions, and then we might get into conservative forces today. We'll see. We do any of these yet? I think we did a few, didn't we? Might tell me which one we left off at. 9, 5 point. Okay. Okay. A ball tied to a string is being whirled around in a circle. What can you say about the work being done by tension? Let me draw a picture. We haven't done circular motion yet, but I think you can probably figure this out. Let's say that I have a guy and he has a rope with a ball tied onto it, and it goes around in a circle like that. Like he's swinging it over his head like a lasso. And I want to know, what is the work done by the tension in the rope? So think about what is the direction of the displacement of this object, and then think about what is the direction of the force, the tension in the rope. And then that'll tell you whether it does no work, negative work, or positive work. All right, I'm going to stop at 120. 120. It's 5 more seconds. Okay, we're sort of all over the ball here, all over the park here. A is the right answer. This might not be clear to you. When we get to circular motion, it'll make more sense. But at a particular point, like say, let's say that I'm dealing with it right here. My displacement is in that direction, right? When it's on the back of the loop, it's in the direction it's traveling in the circle. But my force is always towards the center of the circle. So my displacement is in that direction. My force is towards the center of the circle. Similarly over here, my force in the tension is in that direction, but my displacement is out tangent to the circle, so sort of out of the page there. All right, so those force and that displacement are always going to be perpendicular to one another. That means that it'll do no work at all. So the answer is A. It's the right answer. All right. By the way, guys, in one of your comments, and I haven't looked through them completely, but I'll when I finish, I'll let you know sort of some of the comments about them. But one of the things that somebody said that they would like to see this sort of for more time. So I want to make sure y'all know that this is online, that there's a link on the website that says concept tests. And so when we finish these in class, I always put them online. That's why I don't usually spend much time sort of on this part, because I usually go over the answer prior, but then later you can go back and look online. All right, on the website, there's a link that says concept test. All right, you lift a book with your hand in such a way that it moves up at constant speed. While it is moving, what is the total work done on the book? Okay, I want you to think about this. We're looking for the total work here. All right, remember work is force times displacement. Remember some forces can have positive work, some forces can have negative work. I also want you to think, so remember that some forces can have positive work, some forces can have negative work, and then the total work would just be the sum of all those forces. I also want you to think about what is the net force on this book. And that should give you some insight as to what is the work. Because the total work that's done on any object is actually the net force times the displacement. So think about that. What are the individual forces doing as to positive or negative work? And then what is the net force acting on the object? Still about 5 more seconds. What is the net force on this object? It's zero, right? We know it's zero because of Newton's second law, that the net force is mass times acceleration, and it says that it's moving up at a constant speed. That means that the velocity is not changing, so the acceleration is 0. Let's do about 5 more seconds. I'll stop at 2:15. Okay, good. That's a lot better. Yeah, D is the right answer. The net work is 0. The hand is doing positive work because the force is in this direction, displacement's in this direction. The weight is doing negative work. And since the velocity is constant, that is the acceleration is 0, these two are going to be equal but opposite, right? Because the force is going to be equal but opposite because the net force is equal to 0. So the total work then will be 0. By what factor does the kinetic energy of a car change when its speed is tripled? If I triple the speed of a car, what happens to its kinetic energy? Remember, kinetic energy is 1/2 mv squared. You will have an equation sheet on this next test. It's on the web page. So as you're working through your homework questions, you might want to just print it out and just take a look at it as you're going on, just so you're familiar with it. All right, I'll stop at 50. Awesome, D is the right answer. If I triple the speed, then I increase the kinetic energy by a factor of 9 because it's squared, that quadratic term. Car number 1 has twice the mass of car number 2, but they both have the same kinetic energy. How do their speeds compare? The kinetic energy is 1/2 mv squared. Effectively what I'm doing here is I'm doubling the mass of one of the cars, but I want to keep the kinetic energy constant. So I want to ask the question of myself, how is the speed different for the other car to make the kinetic energy constant? Because it says they have the same kinetic energy. All right, I'll stop at 120, 120. Just a couple more questions. I'll hand back your test. We'll have a few minutes if you want to look over it. Okay, B is right. If I double the mass and I want to keep this kinetic energy still the same, I'm going to have a root 2 here. Root 2 because I square root 2. The square of square root of 2 is 2. Um, so is that clear to y'all? Does that make sense? This isn't exactly right the way I've written it, but y'all clear on? Okay. All right. Two stones, one twice the mass of the other, are dropped from a cliff. Just before hitting the ground, what is the kinetic energy of the heavy stone compared to the light one? Think about how their velocities compare, and then how do their kinetic energies compare? One's twice the mass of the other. Stop at 40. 35. Oh no, we have 30 here, don't we? I'll stop maybe about 10 or 15 more seconds. Stop at 55, 55. Okay, good. D is the right answer. Just looking at the relationships, right? We have 1/2 mv squared. If one has twice the mass, that means that the kinetic energy is twice as much. So uh, it's just a simple linear relationship. So D is the right answer. They're going to have both the same speed, by the way, right? Because it doesn't matter on the mass. They both experience the same acceleration. Previous question, what is the final speed? Let's answer this for you. All right, just about 5 more seconds. Up at 32. Okay, so remember, same acceleration, dropping two objects, they both experience the same acceleration, so they both fall at the same rate, their velocities increase at the same rate. It takes the same amount of time for them to fall, and then they find the same final speed when they get to the bottom. Doesn't matter about their mass, it doesn't affect their acceleration. Okay. How about this scenario of a child that goes from 2 to 3 meters per second? Have they had positive, negative, or zero work done on them? I'll stop at 38, 38. Okay, awesome. A is right. Let's see, if I told y'all this one. Why does the gingerbread man never go to the beach? He has crummy legs. Have I told y'all that one? Oh, okay. That's an alright one. It might not be up to 97%, but it was an easy question. Alright, so positive work here is done because he's speeding up, right? Work-energy theorem. Work equals change in energy. Here I've had an increase in energy, so delta E is positive. So that means I've done positive work. All right, a car starts from rest and accelerates to 30 miles an hour. Later it gets on a highway and accelerates to 60 miles an hour. Which takes more energy, to go from 0 to 30 or 30 to 60? Think about your kinetic energy. All right, I'll stop at 45, 45. Okay, we're all over the board here. Let me remind you that this function, if I plot kinetic energy versus velocity, that it looks like this. So if I were to say like this would be 0, this would be 30, or excuse me, that's kinetic energy, I'm sorry. This would be 0, this would be 30, this would be 60. I want to know which requires more energy, to go from 0 to 30 or 30 to 60. Why don't y'all try that one again? I'll stop at 18, 18. Okay, awesome. B is the right answer. Uh, to go faster speeds requires a lot more energy. That's part of the reason that your gas mileage goes down as you go faster. I mean, part of the reason just that your car is designed to get optimal gas mileage, you know, at a certain speed. It used to be, I think, 45 miles an hour. I expect it's higher than that now. And as you go faster and faster, it just takes more energy because of this relationship between the kinetic energy and v squared. As you go faster and faster, that goes up a lot. All right, let's see. I think we'll probably stop with that one. Let me see what this next one. Let's just do this one, then we'll make this the last one. Is it possible for the kinetic energy of an object to be negative? All right, I'll stop at 28. 28. No is the right answer. Remember, guys, kinetic energy is a scalar quantity, so that would be a hint to you that it can't be negative. But you know, work's a scalar quantity too, and it can be negative. But another thing is that the kinetic energy is 1/2 mv squared. Mass can never be negative. Uh, while your velocity can have a direction and be negative, v here is actually the speed, which doesn't have a sign. But because it's squared, even if it did have a sign, it would go away. Right, so the kinetic energy will always be a positive value. Uh, in fact, energies will always be positive values. It's only our work, and that's sort of an oddball. The work can be negative, denoting that it takes away or gives energy. All right, I'm going to pull up the multiple choice answers. The solutions are on the website. But you know, I don't mark off your multiple choice answers, but you can go through your form and find the go through the form. I also want to just make a note here. I had listed the point distribution incorrectly because I had listed the free responses being worth 70 points, but they were in fact worth 60 points. I tried to mark this on most of yours. If I didn't, I'm sorry. I think I got everybody's. But problem number 17 had been worth 25 points, but I made it just worth 20 points. And problem number 18 had been worth um, 15 points. I made it just worth 10. So if your points don't add up quite right, that's why, because I made those two worth 5 points fewer, the last two. Um, and then there's your multiple choice. You can check them off on your form, which I'm about to hand back now, and then I'll hand back the test. All right, so just come on up. These aren't in alphabetical order. Just come up when I call your name. Lazarus, Gary, Zachary Adamites, Zachary Hanley, Janae, Kayla, James, Tamara, Casey, Sydney, Steve, Zane, and Brandon Domingue. Gary. But don't leave yet. I still have one more. Zachary.